So we look at 9.1 in Precalculus 30 here. What we're exploring is rational functions. We've taken a look at all kinds of functions: exponential, logarithmic, quadratic, cubic, quartic, linear, all sorts of stuff. We are now talking about rational functions, and we're going to talk a little bit about transformations and how rational functions can be altered, right? Their position, their shape, their orientation, using transformations that we've studied all year. So, first of all, what's a rational function? The root of the word rational is ratio. Okay, ratio. So it is literally a ratio of functions. Look down here on your page. What is this? Page 430. This is the definition of a rational function. Okay, you don't have to copy this word for word, but let's just talk about it for a second. A function that can be written in this form, where the f of x, the function itself, is written as a ratio of two other functions. Now, the p of x can be a monomial, binomial, trinomial, whatever, and it also can be just a constant number, like 5 or -1. The q of x, that's the one in the denominator. There's two things, though, that it has to be. Okay, first of all, there is an x in this function. Girls, you all right? Okay, disaster? No?
Kind of.
Kind of?
Yeah, someone has. It's fine. It doesn't matter. There's something.
All right, so q of x has to be a polynomial that has an x in it. Everyone listen to that? So it can't be just a constant. That's not a rational function. This q of x has to have an x in it. So notice the examples here. 20 over x. There's a constant on top, but there's a polynomial as a monomial with x in it. Here's a monomial with n in it. Here's a binomial with a variable in it. So these are all examples. Also, the value of this function cannot be 0 itself. Okay, you can't divide by 0. That's obvious. But this q of x needs to have an x or the variable in it. Okay, that's kind of what makes the rational function special. All right. So let's take a look then. This is kind of an abbreviated lesson here on this one. So let's take a look at the parameters of y equals a over x minus h plus k. All right. We're going to start with y equals 1 over x. So grab your graphing calculators, and I want you to punch this in: y equals 1 over x. All right. So on your graphic calculator, I want you to plug in y equals 1 over x. Now, in the textbook asks us to compare this with y equals 4 over x. So I will do this on Desmos here, but I want you also to plug this in simultaneously, and we'll see what happens. So go ahead and do that. And on this second graph of mine, I am going to move a from 1 to positive 4. So see what happens. There it is. The blue graph is going all the way up. Whoops, sorry. All the way up to positive. There's 3, 3.5, up to 4. Okay. So what has happened here? Let's back that off a bit. Can you guys see that in the back? Let me brighten things up for you. All right, so this number right here on the red graph, if x equals 1, what is y? Should be 1. Let's see. Look at that. 1, 1. Okay. Now, if we have moved a is not 1 anymore, but a is 4, so that's y equals 4 over x. What does a usually do for transformations? Vertically stretch. So let's just see if we follow this x up here. Let's see what this point is. And it is, look at that, 1, 4. So a is vertical stretch. Got it? Okay. Okay, let's move a back down to 1. Look at that. Isn't that kind of cool? I like that. Whoa. What happened there? Look at this. Look at that. It's kind of like some weird Egyptian dance there. See that? Walk like an Egyptian. Dance like a rational equation. Okay, so a is 1. All right, so what are we working on next? What's the next parameter you want to test? How about h? Lovely. Okay, so what do you think h is going to do based on what you know about transformations? Horizontal what? Stretch? Horizontal translation. Okay. H, look at that. It goes right. Isn't that neat? That is just visually pleasing. I'm not sure why. Look at that. That's awesome. I like that. Okay, so h, if h is 6.7, every point is translated to the right 6.7 units. Now notice it's going to show up as 1 over x minus 6.7, right? Because it's minus the positive value. So 1 over this red graph is 1 over, sorry, the blue graph, x minus 6.7. Okay, got it?
Is the asymptote vertically?
Okay, vertical asymptote. We haven't got to the vertical asymptote yet, but there is a vertical asymptote here, yes. Now, if you remember from years past, when we have a function where there is an x in the denominator, okay, there are going to be some restrictions on the variable x. Right, Tony? You with me? Tony? Wake up, Tony. All right. There's going to be some restrictions on x. So x cannot be 0, right? So that's simply the restriction. X cannot be 0 here. So what is x equals 0 in this function? What does that represent? Well, if there's no x to divide out as a common factor, then if it's all by itself in here, and this is the simplified version, then x equals 0 is our vertical asymptote. Okay, so you guys probably know that already. But let's take a look. See, x equals 0, vertical asymptote. So if I move this over, so h value, I move it over, the vertical asymptote moves as well. So here is h equals 5. Look at that. Vertical asymptote moves over. Okay? Does that make sense? Questions?
Yeah.
Yes. So this blue graph, if I look at that, I'll get rid of the h, the red graph. Look at, see the vertical asymptote is x equals 5. And in this case, the equation here is actually y equals 1 over, see, 1 over x minus 5. That's what this equation is for this graph. All right, so the vertical asymptote just moves. Okay, very good. So let's go back to it. What happens then? Oops, 0. What happens with k? All right, that's going to be a vertical displacement, up, down. Vertical displacement. Got it? So h, there's h moving left, right. Here's k moving also up, down, left, right. So there you go. Kind of one of those. That's pretty weird, eh? Let's let a move too. See what happens. Whoa. Cool. A is negative. So obviously, what happens to a if a is negative here? It's going to. Okay. Stop. 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 Oh, that was weird. Okay, let's bring it over here. So yeah. Stop. So if A is negative, it flips around the other way. So what is that a reflection of? It's a reflection about the what?
X and Y.
So X and Y flip? So is it a reflection about an axis or about a line? Okay, let's make h 0. Let's make k 0. Okay, let's make this just negative 1. Whoa. Negative 1? No thanks. Negative 1. Okay, so is it, I don't know, is it the inverse? What do you guys think? I don't know if it's the inverse because here's the x equals y line. So, you know, really, the inverse, this is going to be its own inverse, really. So what does that, how does that change? Interesting, eh? So it's, I'll let you guys think about that. Okay? Is it, and I'll move the, look at this. So what's happening? Okay, there's original and, okay. How is that? Maybe you can describe it as a rotation. I don't know. Right? Maybe something else. Okay, I'll let you think about it. Maybe you'll come across that in the lesson here. All right. So if we go back to our lesson here, graph using a table of values. Okay, you could do that. No problem. 10 over x. You plug in negative 100. What's that? Well, negative 0.01 when you get to your y. That's easy stuff. So this is just kind of what it looks like. Here's some characteristics of rational functions right here. And this example right here is a very good one. This gives us a little bit of a snapshot of what the parameters do. So compared to, without looking at the answer there, compared to y equals 1 over x, what is happening to that graph? How is it being transformed? What does this 6 do to it? Vertical stretch. Good. What about the negative 2 here, x minus 2? What does that mean? Moves where, Jaya?
Vertical stretch moves.
Where does this x minus 2, what does that do to the graph?
It moves it to the right.
To the right 2 units. Good. What about this minus 3 out here? What does that do, Melanie?
It moves to the vertical stretch.
Vertical displacement. Which way? Up or down? Down. 3 units. Okay. So here's the answer. Look at this. They started with 1 over x right here. And they stretched it. So this point, for example, stretched by a factor of 6. Then they moved it, looks like 1, 2 units to the right and 1, 2, 3 units down to get this final green graph. Okay? Now, what about horizontal asymptotes? Yeah. What's the horizontal asymptote for this graph? 0. Yeah, it is. What if A, okay, so let's get rid of this. What if A is something different? What if A is something different? What's the horizontal asymptote as I move this? It appears still to be 0, right? And what about over here? Yeah, still 0. So it's important to note that this type of rational function has a horizontal asymptote of 0, and I'm just going to give you a couple hints, okay, for this. So, there's some text here. Let's make it black. Okay, so copy these down. You notice this is a little bit of a hint as far as horizontal asymptotes. If the degree of the function in the numerator is less than that of the denominator, then the horizontal asymptote is always y equals 0. So that's just a little bit of a shortcut. So if I have this right here, like this, the degree in the numerator is less, then it's y equals 0. Like this, y equals 0. Like this, 2x to the 10 over 2x to the 11, y equals 0. Okay, if the degree is less than the top. Now, I don't know if in this section, I don't know if we'll get into horizontal asymptotes, other horizontal asymptotes, but if you know that for now, that's good for now. Example goes though, without talking about horizontal asymptotes right now, but this leads me to my next point here. It looks like we have a vertical asymptote at where? At x equals negative 2. That's what it looks like, because I have a restricted value in the denominator. X equals negative 2 would make this a 0. Now there's a bit of an exception here, because let's just sketch this out here. Okay? Back to normality. So why is that? Because, check it out. If we simplify this, and how would we try and simplify this? Factor. Very good. So what are the factors up top here? X plus 1 times x plus 2. So if you have a common factor from the top and the bottom, please note that x equals negative 2 is still restricted. It's still naughty. You cannot use it. It does. If you plug x equals negative 2 into this, your calculator will not like you. It'll say there's no answer because it's a restricted value. But does it mean there's a vertical asymptote? No. If you can simplify the rational function and come up and you can divide out common factors like this, and so there ends up to be nothing, look what happens. Y equals x plus 1 is the simplified version. And so that's what the graph will look like. And that's what we see over here. See? X, see, up 1 over 1, and going through x equals 1, y equals 1. Now, I try to zoom in on there, and for some functions, actually, am I in projector mode? I am. Okay, let's see if we can do this again, because at x equal, oh, I was at the wrong 2, wasn't I? I was at positive 2. Okay, let's zoom in and see what's happening here, because something should be happening here that it looks like it's a solid line. Let's just see. Let's just see what happens. I'm zooming. I'm like in ant world here now. Now I'm in fungus world in oh! Look at it! This is amazing! Look at what's happening! Look at, we have a disruption in the space-time continuum here. You see this? Now this is really zoomed in here. Look at, it starts to go absolutely schnuts right here. And at x equals -2, we have, it's undefined. There is a serious problem. So it appears to be a straight line, but look at, once you get in there, it ain't. We got problems there. It ain't. It ain't just a regular old straight line. Look at that. Look at, you'd never know, would ya? I should do some Twilight Zone music or something. Look at him, coming back out, back out. Look at that. See? Here's real world. You'd never know what's right in there. It's like what's hidden deep inside your DNA. That's what it's like. Okay? So that's what happens. Any questions about that? There's a question asked, what about the transformations, A, H, and K and stuff? You wouldn't be able to look at this and say, there's a clear kind of parent function here and I'm just applying changing the parameters. No, this one is a bit more complicated and you wouldn't actually kind of try to figure out what it looks like compared, with these parameters. So don't worry about that. There's, like I say, there's a big section. There's lots of stuff that we're doing here, but this, you would just have to realize that something is wrong at x equals -2, and is it a vertical asymptote, or is it and what that is that we zoomed in on, that's actually a gap. It's actually a gap discontinuity. So the function is not continuous. This is not a continuous function, because it jumps over x equals -2. Okay? And what value would this be? -2, -1. Okay, if we put -2 in here, we would get something close to -1 if we put something close to -2 in here. So this little point right here that should be there, that's not. Okay, you'll notice, look at that. See, at -2 it's undefined. So there is a gap, discontinuity. And in calculus we'll talk in those terms a lot. So I just want to introduce you to that now. It's a gap discontinuity. Of course, this one up here, okay, that discontinuity is a vertical asymptote, right? It's coming and it's going down here and it never touches x equals 0. That's an asymptote. But this one is a gap discontinuity. Right there. So yes, this always doesn't happen. Only when there's a common factor in the numerator and denominator. Let's just check this out. Watch this. If I change this number right here, so watch what's going to happen to this black one. If I change this number right here to something like a 3 where there is no common factor, then what happens is that. So now we have a vertical asymptote at -2. See that? And we do not have a horizontal asymptote. Note. And again, I'll probably get into this in another lesson, because the degree here is larger than the degree down here. So that changes the horizontal asymptote situation. But yes, if there is no common factor and this x plus 2 in simplified form remains in the denominator, that is a vertical asymptote. So again, if I change this back to 2, we do not have a vertical asymptote, we just have a gap. Let's change it to something else. 7. Oh, look at what 7 is. 7, same thing, at -2, vertical asymptote. Okay, at 6, same thing, -2, vertical asymptote. Okay? Good questions. Anything else?
Why is your horizontal one on such an angle?
Okay, why is the horizontal one on such an angle? It's on such an angle because it's not horizontal anymore. It's called an oblique asymptote, and there is a way to find out what the equation of this oblique line would be. It's actually not that hard, but I think I'm going to save that for another lesson for you. But one of the shortcuts that I will mention is that when this degree in the numerator is larger than this degree, you have an oblique or slant asymptote. Okay? Very good. And what happens if this degree was the same? Well, let's just take a look. Let's see. Let's square that. Scandalous. Okay? Where does there appear to be a horizontal asymptote? Does there appear to be one? You know what? You can't actually look in the middle of the function for a horizontal asymptote. What you have to do is you have to go very far to the right or very far to the left, like I'm doing right now. And what number does this seem to be close to? In the y value, pretty close to 1. Interesting. So if we're talking about asymptotes, when the degree is the same, the horizontal asymptote is equal to what? Any guesses? Not always 1, no. Watch this, watch this, watch this. I will help you. Let's make that a 3. Let's make this a 2. Oh, what is this? Pretty close to what for a y value? 1.5. Pretty close to 1.5. Is it getting closer? Yep, a little closer to 1.5. Where do you see 1.5 in this equation? Anywhere? 3 divided by 2. So, I wasn't going to do this today, but you guys are just begging for it. When the degrees are the same, the horizontal asymptote is the ratio of the leading coefficients of each polynomial. Oh, beautiful. And yes, I learned this. Not scandalous, no. And yes, I learned this about, 26 years ago. Yes, I did. Okay? And yes, I had to write a test on it like a week after I learned it. Yes. Yes. But once you've been doing it for 26 years, you'll be way better at it. Just think, if you're still doing this in 26 years, A, I will laugh very hard, and B, 26 years, I'll be like 175. You can come visit me in the old folks' home and share with me all of your excitement about teaching this stuff. So, hey, Mr. Maxwell, remember when you taught me this like 26 years ago? I'll say, no, who are you? Get out! That's probably what I'll say.